All right, guys, how we doing? Back at you with another lecture video here for chapter 15. All right, so starting us out, kind of pick up where we left off with. If we look back here, we were doing some examples of, using table I here, right? Table I is pretty important. Go back and find table I. Here we go. Right, table I is important. Got a lot of really useful information on there. Pretty much every single reaction you're going to be looking at throughout this chapter is going to be coming from table I. And if for some reason it's not going to be on table I, they're also going to provide you the delta H value in kilojoules, right? Whether it's positive or negative, right? Because obviously you'll need that positive or negative sign to help you determine if something is endothermic or exothermic, right? So skipping back ahead to where we're supposed to be at today. Here we go. Now, I mentioned in class the other day and in the lecture video that when it comes to enthalpy and delta H values, right, and in thermal chemistry in general, a lot of what we're going to be doing is based on chemical reactions that are taking place, right? And that rung true absolutely in your guys' most recent lab you guys just did for that heat of reaction lab, right? You mix some HCl, you mix some NaOH, right? Water as well in a couple of reactions, right? Those NaOH white pellets, mix those with water for sure. So you guys ran some, chemical reactions, right? 3 different reactions, and those were chemical reactions, right? And then you were able to measure the temperature change and then run some calculations to see what the actual delta H value is going to end up being from those changes in temperature, right? Chemical reactions. Now, this quick slide here is more so talking about the physical change aspect of enthalpy. There isn't really going to be too much of a calculation regarding these physical changes here in your delta H values, but this is more so just going to be trying to determine the type of process that it is whenever you're encountering any of these physical changes, right? So physical changes, in this case specifically, we're talking about phase changes, right? So things like melting, boiling, sublimation, or heating, these are all going to be endothermic processes, right? Because if you're melting something, right, think about an ice cube, for example, right? You're going to melt an ice cube from the solid state to the liquid state. In order to melt that thing, you've got to raise the temperature of it, and that's going to also be a situation where when the temperature is being raised on that, or for that ice cube, you're adding heat, right? Heat is being added to that ice cube. That's slowly allowing it to transition from a solid to a liquid. And that's going to always be an endothermic process, right? Because remember, endo, enter in terms of heat. So heat is entering that system or that thing you're viewing, right? Same with boiling, same with sublimation, and generally all kinds of physical changes where you're heating something up too. Now, when it comes to our phase changes like freezing, condensing, and deposition, right, it's going to be a totally opposite thing, right? These are all exothermic processes, right? So let's think about freezing, for example. If you want to make ice cubes, for example, right, maybe you've got a little ice tray that you filled up with some water from your sink, and you're going to go ahead and pop that ice tray into your freezer, come back 2 hours later, and you're going to now see you've essentially created, right? The water underwent a phase change from liquid to solid, and in doing that, freezing it from a liquid to a solid, you've essentially extracted the heat energy from that liquid water, causing it to be an exothermic process, right? So from that water, heat was exiting that water or exiting the system. So remember, exothermic, exit, exit in terms of what the direction is heat. So heat is being removed in these exothermic processes. So please don't forget about these. I would definitely mark this slide as important in some capacity, right? Because knowing and understanding melting, boiling, and sublimation, and freezing, condensing, and deposition as either endo or exothermic processes is going to be really, really important for you guys. Okay. Now, when it comes to enthalpy and potential energy, it's going to be a little bit of a different conversation here. We're going to be using this idea here to actually show and add to what's known as a potential energy diagram. Now, I know last chapter we dealt with a couple of different diagrams, but this chapter is going to be no different in terms of looking at a diagram and also being able to label one as well. The change in potential energy / enthalpy can be shown on a potential energy diagram, and enthalpy is the same thing as the change in potential energy as well, right? So delta H is basically the same thing as potential energy. So let's go ahead and take a look at some examples of this. In class, actually, there's a big part in your in your notes where there's a giant potential energy curve, potential energy diagram that in class we're going to take care of. But for right now, let's look at just a basic potential energy diagram. So when it comes to a potential energy diagram at its most basic form, of course, when any diagram, you've got an x and a y-axis. Now, looking at the x-axis here, the x-axis for a potential energy diagram is labeled as the reaction coordinate. Now, the reaction coordinate just basically indicates the progress of that reaction. Sometimes also just straight up labeled as time to make things a little bit simpler. But reaction coordinate, guys, is just a basic, or is a little bit more of a different way of saying just plain old time, right? So from the far left over here, right towards the center of the axis, all the way as we progress left to right here is the reaction coordinate going left to right. And that's the same thing as if time was going by, essentially, right? So reaction coordinate, or essentially time for the x-axis. Now the y-axis is, of course, going to be energy. In this case, potential energy. Now, a couple of things to note when it comes to the y-axis here. The higher your energy, the less stable this particular reaction is going to be, right? So when your energy is much, much, much higher on the y-axis on these potential energy diagrams, that's going to exhibit some more unstable characteristics. Whereas, of course, the lower the energy is in that curve, the more stable that particular reaction is going to be, right? So it's all kind of based on stability in terms of where the energy is at. Now, speaking of energy, is a concept known as activation energy. Now, activation energy is also associated with these potential energy diagrams. So we're gonna loop this in class when I talk to you guys next. Okay, so activation energy. It's called the minimum amount of energy required to get a reaction started. Guys, every single reaction that ever exists ever in our world when it comes to chemical reactions is all going to be require some amount of energy to actually get started. So if we look at this diagram down here, right, I'm actually going to even trace it as well. So we look here, and here's my little cursor here, right? So at the start here, we've got this little curve here, and as we start, we're starting out at this energy here. And then eventually, as we continue down this reaction is going to need more energy to actually occur here, okay? And being able to have that particular reaction have the required energy to get over that hump there, this portion of the curve here, that's known as your activation energy. Now again, every single chemical reaction has some required amount of activation energy to actually get that reaction started. Oftentimes it just comes from the reaction itself. Other times it has to come from an external source, like maybe a battery or some other form of energy to kind of give it a jump start, okay? Now, on top of that activation energy is also something very similarly called to that, which is known as the activated complex. So there's activation energy, and then there's activated complex. They're not the same thing, but they kind of do mix with each other a little bit here. So the activated complex, sometimes referred to as the transition state, but rarely will you hear that. You'll most often than not just hear called as the activation complex, is the temporary unstable arrangement of atoms where old bonds are breaking and new bonds are being formed, right? And of course, that's the point in time where you've got a bunch of your reactants turning into products, and there's kind of just a whole mix or an amalgamation of all the different atoms present in those reactions. They're just kind of mixed. And there's no real new bonds being formed just yet, but it's sort of a process. It's almost like the halfway point between when those reactants turn into the products. Okay. This activated complex occurs at the height of the potential energy diagram, sometimes also referred to as the intermediate. So if I still look at this particular picture at the bottom of your screen here, guys, this activated complex occurs at the highest point on the curve, which happens to be right there. Now that wasn't the greatest little orange dot there, but this right here, right, this orange dot right here is the highest point on the curve. So the highest point on any single curve, whenever we talk about these potential energy diagrams, guys, is going to be your activation, your activated complex. Okay, so it's the highest point on a potential energy diagram. Now, when it comes to potential energy diagrams, you can actually look at the potential energy diagram and look at the location of the curve, where it's starting, where it's ending, and everything in between, to kind of help you determine if something is considered an endothermic or an exothermic reaction. So I've got two pictures there, and we're going to talk about it a bit here, right? in an exothermic reaction, the potential energy of the products is less than the potential energy of the reactants. And we can see that right here in this particular picture on the left here, right? So our reactants are way, way up higher at a higher energy than our products are, right? Products are at a much, much lower energy. So when your reactants are higher up in energy than your products are on the right, that's going to give rise to an exothermic reaction. Well, if I continue down that road there and talk about an endothermic reaction, it's going to kind of be the opposite, right? The potential energy of the products is then going to instead be greater than the potential energy of the reactants, right? So if we're looking at the right-hand side picture now, the endothermic reaction here, all the reactants, excuse me, on the left-hand side here, right, have a much lower energy than our products on the right-hand side of this curve here. So as you notice this curve going from left to right here, again, my very, very horrible drawing there with my line, again, the energy of our reactants is much, much, much lower than the energy of our products, which is much, much, much higher, okay? So that's one of the best, if not the best, way to determine if a potential energy diagram is either an exothermic reaction or an endothermic reaction, right? Pretty basic. So look out for where the reactants and the products are. Now, reversible reactions. This kind of gets into something that I've talked about briefly in the past. It's going to actually be the main crux of the second half of this chapter, chapter 15 here. So let's kind of get a little bit into it here. Basically, up until, I want to say every single lab you guys have done where you've done some chemical reaction, every reaction you guys have ran had a starting point and an ending point, right? You took your reactants, mixed them together, and then eventually created some products. And there was nothing you could do. Once you created your products, there was really nothing you could do to get your reactants back, right? That'd almost be like if I've talked about this in the past, right? When we first talked about chemical reactions, that'd be like if you took all of your baking ingredients, right? Your eggs, your water, your flour, your sugar, your butter, any of those things that you use to bake, mix everything together, pour it into your cake tin, through the cake tin or muffins or whatever, right? Cupcakes, threw it into the oven, and then got your cake as your final product, or your cupcakes or your bread or whatever as your final product, and then tried to take that cake or muffin or cupcake or bread and then turn it back into a bunch of flour or water and bread and sugar and all that stuff and eggs, right? You can't do that, right? A lot of chemical reactions in life, you are not able to reverse it, where you take your product that you ended with and turn it back into your reactants. However, there are absolutely some reactions in chemistry that are in fact reversible. And again, this is going to be the main crux in driving conversation for the second half of this chapter here. So we're going to kind of get into it a little bit here. So the reverse of an exothermic reaction is an endothermic reaction, right? So if you have to start out with a reaction where your reactants are forming your products, that's exothermic. Well, if you reverse it and have your products turn back into their reactants, that's going to cause, in turn, be the opposite, which of course is an endothermic reaction, right? So in that case, you're going to actually reverse the sign on your delta H. And of course, then the reverse of an endothermic reaction is then going to be an exothermic reaction, which would then require you to reverse that sign on your delta H value as well. Okay. So with that being said, guys, I will see you back in class with some example problems. All right. See you then.